Okay, this is Mr. Baker. We're going to take a look at the exponentials and logarithms review sheet that we've got for the end of course test. This front slide right here, top left on your worksheet, has lots of formulas, changing back and forth to logarithms, future value, that's our exponential growth, some rules of exponents. These will not be given to you on the formula sheet, so make sure those are all committed to memory. This first question, which expression is equivalent to 18 times 3 to the n plus 2? There's a couple ways to do this problem. One way would be to just plug in for n, just pick a number. I like to pick 7 if I'm going to do that. See what value this all gives us. And after that, plug in the same number for all of these n's. That'll be a really big number, maybe even scientific notation, but that's okay. That'll work. Now, that's not the way I chose to do it because it's not the fastest way, and it's not the way it's really intended to be. The idea here is, since this is 3 to a power being multiplied by 18, this is all multiplication. So let's see what that 18 is made up of. If we just factor it down, we get 2 times 3 times 3, which is still being multiplied by 3 to the n plus 2. Well, another name for this 3 times 3 would be 3 squared. Well, looking at it right here, we've got two different powers of 3. And what do we do when we multiply powers with the same base? Well, we're going to add their exponent. So that's going to be 3 to the 2 plus n plus 2. And we've done plenty of that adding exponents before. And we've seen it look like this, but we haven't done a whole lot, certainly not in a while on that. But we should be able to do 2 plus n plus 2. That's just going to be n plus 4, combined like terms. And that's one of our answers. That is B. And that's all we needed to do. So that's two different ways we can factor down that coefficient so we can combine powers of the same base. Or we could, if we got stuck on it, plug in that 7 that I like to use. And let the calculator do the legwork for us. Let's look at number 2. It's a very similar problem, but this time we've got 81 to the 2x equals 9 to the x plus 4. Well, just finding something equivalent isn't something we did a whole lot of, but we certainly solved equations that looked like this. And our first step was to make our bases the same. So let's look at some things. Start with that 81. What's another way to write 81 as a power of something? Well, 81 is really, what's 9 squared? We should know our squares off the top of our head. Hopefully you look at 81 and you think 9 times 9. But there's another way to do it. Since 9 itself is 3 squared, that means 9 squared is 3 squared squared, or 3 to the 4th power. So it's two different ways we could write that 81. Similarly, we can take that 9, that's the base of the other side of the equation, and write it as 3 squared. Well, how does that help us? Well, all we're really doing on this, we're looking for equivalent equations, by the way, which means we can't just plug in a number for x, because since it's already an equation, there's only one value of x that's going to make that work. So we're going to have to go with a different technique, and that's where this changing bases comes in. If you look at the last two answers, everything's got a base of 9 on the last two answers. Well, the right side already has a base of 9. This left side, we can change it to be a base of 9 because we know 81 is equal to 9 squared. So we can make that 9 squared to the 2x equals 9 to the x plus 4. And when we raise a power to a power, what do we do with the exponents? We multiply them. So it's 9 to the 4x equals 9 to the x plus 4, 2 times 2x. And that's one of our answers. That is F. Well, if F is an answer, if we look at E, E is almost the same thing, just that 2x versus the 4x. Well, if F is our answer, E can't possibly be. There's nothing I can change. Now, if it had been 9 squared to the 2x, like we had written here, then yeah, they could both be answers. But that's not what we've got, so it's definitely not E. Well, get that out of the way and maybe look at the rest of these answers. All have 3 as the base. So we're going to need to rewrite our bases as 3. 81 is 3 to the 4th. 9 is 3 squared. So where if we got an 81, we put a 3 to the 4th. Where we got a 9, we put 3 squared and get that. Again, when you raise a power to a power, you multiply the exponents. Don't forget to distribute if there's addition in those exponents. That's going to be 3 to the 8x equals, that's supposed to say 3. That's a typo on my part. 3 to the 2x plus 8, which is that answer right there. It's D. Well, that means if you look at the rest of these, they all have too much in common to be just a change on that D answer. So all those are wrong. And we've got our 2 answers. Remember, when you've got more than 4 options, there's a good chance more than one of them will be. Let's look at number 3. This is going to be a pretty easy problem, and I expect to see something similar to this. We've seen some problems with these boxes where we got to fill in the boxes before. Each day, Julian deposits 2 times as much money as he did the day before into his savings account. His initial deposit is $6. Drag a value to each box to complete the equation to model the deposit Y on day X. So in other words, the deposit is Y, that's what Y equals. Our day is X. We got the first day, the second day, the third day. Arguably, you could also have day 0, and that's the way I want to think about it. But we've got 3 different boxes here to fill in for, and each one has a job in an exponential equation. And we've talked about this before. The first one is our starting amount. That's the coefficient. Now, the base of the exponential, that's what our growth factor is, what we're multiplying by each time. And the exponent is how many times we're multiplying by that growth factor. So each one of these is represented somewhere in this sentence or this paragraph. So let's look at the first one, our starting amount. Well, our starting amount is an initial deposit, that's $6, so that starting amount is going to be 6. The next piece, the growth factor. Well, what are we multiplying by each time? Well, it said that too. Each time we deposit 2 times as much money, which means that's going to be 2. And because we're going to multiply by 2 every new day. And speaking of days, that's how many times we're multiplying. If we're on the 5th day, we're going to multiply it 5 times. So it's on day X. Well, that must mean that X is our exponent there. Now, there's an argument to say that, hey, if we're going to start on day 1, that our starting number wouldn't be 6, but would be 3. Why? Because if this was a 1, if we wanted our first amount to be 6, it would have to be 3 times 2 to the 1. It's not real clear if our first day is day 1 or day 0. This is the way I would go. Typically, our initial amount, our starting amount is 0. But that's arguably also a correct answer, which means this question, not a complete question. It's not clear, it's not clarified, or maybe they'd accept either answer. I don't know. I'm not the state. But this is definitely, a valid working of this problem. Okay, number 4. The change in the population of fruit flies can be modeled by the equation P of t equals 3 times 1.5 to the t. So it gives us the equation where t is the time in days. It's notable that it's in days. Usually in this equation, that's going to be in years, but since all of these say daily, it doesn't really matter anyway. Which statement describes the change in the population of fruit flies? Well, this is actually based on our future value equation, and we can tell that because they're asking about these percent increases or decrease. But there's our equation right there. Future value equals p times 1 plus r to the n. So our p, our principal, our starting amount is 3. Our base of our exponential is this 1.5. and our n exponent is actually, well, t for time. But the part that we're interested in, we're looking for the rate, which means 1 plus r. And what's a 1 plus r? Well, that's the thing being raised to the power. So that's going to be our 1.50. But if we're actually looking for the rate, remember the 1 is part of that base, so we got to get rid of that. So let's just subtract both sides, take 1 away from both sides, and that's going to leave us with 0.50. And what's that as a percent? Well, that's 50%. Well, there's only one of these answers that had 50%, and that is C. It's also worth noting that since our base was bigger than 1, 1.50, it couldn't be a decrease. A decrease would be less than 1 for the base. So we already had it narrowed down between B and C. But yeah, it'd be really tempting to go with that B because 1.50 is 1.5, but not 1.5%. We need to remember that our base is 1 plus our rate, and we just have to subtract that 1. If this had been a percent decrease, then that would have come out as something less than 1. We'd still subtract 1 from it, and our rate would have come out negative in that case. Doesn't mean we report the rate as negative. Just saying it's a decrease is already enough to know that it's going to act like a negative. All right, number 5. What is the solution to this equation? It gave us an equation to the nearest hundredth. Now, there's a lot of ways to solve this. Some ways we've talked about before. We could graph the left side as y1, the right side as y2, and find where they cross. As a matter of fact, I think we had a problem like that on a worksheet a while back when we were learning that trick. But really, this isn't that hard. If we're trying to get this solved, that means we want to find h. Well, right now it's in an exponent. The only way we have to get that out of an exponent is to transform it into a logarithm. So if we're going to transform that into a logarithm, well, we just got to know where the different pieces go. So there's going to be a log base something of something equals something. So let's start with this question. What's the base going to be? Well, the base of your logarithm is the same as your base of the exponential. So it's going to be log base 10. It's always nice to have base 10 because you don't have to type a base in on the calculator. If you just hit that log button, it's automatically log base 10. Let's jump to the other side of the equal sign because we know a log is always going to be equal to what? Well, the log should be equal to the exponent. Logs are equal to exponents. Logs give us exponents. So that exponent is 2h. That's what's going to be on the other side of the equal sign. But we've got to take the log of something. We can't just have a log by itself. What do we take the log of? Well, the only other number here is 45. So that's log base 10 of 45 equals 2h. Well, log base 10 of 45, that's just a number. You don't have to be scared of that number. Put that in your calculator, and it should spit out 1.6532. Keep a bunch of decimal places so you don't have to worry about the rounding. And that's still equal to 2h. And now we just divide by 2 on both sides. H equals 0.8266. Well, it says round to the nearest hundredth. That's 2 decimal places, so that's going to be 8.3. Number 6 is another future value problem. FV equals P times 1 plus R to the N. Not so much compound interest as compound appreciation. We could also have depreciation. So let's see. But instead of FV, we're going to use F of T. For the rest of it, we're going to have to read the paragraph. Stacy owns a collection of dolls for the 19th century, currently valued at $67,000. That's a nice little investment there, I'm sure. The value increases by 12.5% annually. Which function represents the value of the doll collection after T years? Well, we got to know what goes in each place. Let's start with a P. Now, that's our principal. That's our starting amount. Well, that's the 67,000. So 67,000 is our coefficient. Next up, it's worth noting that this is an increase, it's not depreciation, it's going up, which means it's 1 plus. Now, if it was losing value like a car or a computer would, it would be 1 minus the rate. But it's not, so it's 1 plus. So what is our rate? Well, our rate is 12.5%. Of course, we don't plug it in as 12.5. We've got to make a decimal out of it. Move that decimal point 2 places to the left. It's 0.125. And it's after t years, and it's annually, so every year we're going to multiply by that 1 plus 0.125. So our n is just going to be that t number of years. Combine that up in the parentheses. It's not very far to go to get 67,000 times 1.125 to the t. Now, if you look at these, b would be if it was some sort of a depreciation, although even the numbers don't quite line up there. I think that would be 0.152 subtracted, 0.143, I don't know, something like that. I guess I should take the time to subtract it before I talk about it. But it's depreciation. The simple fact that it increases means our base has got to be bigger than 1. So b is out and a is out. And honestly, d is just way too big a base. That would be an 8,000 something percent increase. So we could probably get to this one by the process of elimination, but this is also the type of problem that they may want us to write this on our own. So knowing how to work with this future value formula is going to be very important to us. We'll definitely see that pop up somewhere on the test. Okay, finally, number 7. We got 2 parts to this one. It gives us the logarithmic equation and says which process should be done first to find the correct value of x in the equation. And then it does ask us to finish solving for it. Well, the only way we really got to solve logarithmic equations is to transform them into exponential equations. There's really nothing else that we've ever done in our class to do that. That doesn't mean there's nothing else that could be done, but that's as far as we've ever taken logs, because that's where the standards take us. So if we look at these, rewrite the logarithmic equation as a natural log equation, well, no, we're not going to do that. It's already got a log. We're not going to put another log on it. Take the log base 10 of each side. Well, we've already got the log base 10 of one side. If it was 10 to a power, that might have been an option. Take the inverse natural log of each side. Well, what does that even mean? Well, that means make both sides into exponents of e, but we don't want an exponent of e. We want 10 is our base, so that's the only base of an exponential we want to make. D, rewrite the logarithmic equation as an exponential equation. Well, that's the only thing we've done with logarithms, so that's what we're going to do with it here. But now we got to finish solving it, so we do need to build our equation. So transforming from a log to an exponential, kind of backwards of what the last problem did. What's my base going to be? Well, the base is the same as the base of the log. Which is 10. So the base of our exponential is going to be 10. What about our exponent? That's our next piece of an exponential. Well, exponent always comes from the other side of the equal sign, because logs always equal an exponent. So our exponent is going to be 4. And that's going to equal something. Well, there's only one thing left to be equal, and that's what we were taking the log of. So that's going to be 2x minus 2. So 10 to the 4th equals 2x minus 2. Well, fortunately, 10 to the 4th is just a number. It's just 1 with 4 zeros after it, 10,000. So 10,000 equals 2x minus 2. That's something we can solve. Get x by itself, so what do? We add 2 to both sides, gives us 10,002 equals 2x. Then divide both sides by 2. 5,001 equals x, and that's going to be our answer. I hope this helps you remember what we did with the exponentials and logarithms. If you've got more questions, hopefully we've got time in class to field them. And remember that this is going to be part of a quiz grade on Tuesday. And good luck.